This film is about an andesite volcano, the Soufriere Hills volcano on the island of Montserrat in the Caribbean. The objectives of the film are to tell the story of the eruption, explain the volcanic phenomena and their hazardous effects, and to describe the modern methods of monitoring an active volcano. The Soufriere Hills provides a superb example of island arc volcanism, with a remarkable diversity of volcanic phenomena. You will experience great spectacles of nature, including the growth of a large andesite lava dome, pyroclastic flows and surges, explosions, ashfall, a large volcanic landslide, and volcanic mudflows. You will learn about the processes that cause andesite volcanism and the geological and geomorphological and human consequences of a major andesite eruption. You will appreciate how modern geophysical techniques that monitor earthquakes, ground deformation and volcanic gas emissions are transforming our understanding of volcanoes and the ability to forecast their behaviour. The island of Montserrat in the eastern Caribbean is seen here viewed from the north. The island lies at the northern end of the Lesser Antilles island arc, a chain of islands with 11 active volcanoes from Grenada in the south to Sabre in the north. Montserrat is an island of about 80 square kilometres, with the Soufriere Hills volcano occupying the southern half of the island. To understand island arc volcanoes, we have first to go to the ocean ridges, where tectonic plates are created by seafloor spreading. The plates split apart and move away from one another. At the ocean ridges, basalt volcanoes erupt at the crest of the ridge. On the mid-Atlantic ridge, over 2,000 kilometres to the east of Montserrat, seawater meets the basalt magma, and water at 350 degrees centigrade spurts out in violent hot springs on the sea floor. These are known as black smokers. The basalt lava that makes up the ocean crust is hydrated, and this is the key to understanding why andesite volcanoes like the Soufriere Hills exist. The Atlantic tectonic plate is subducted below the Caribbean plate at 2.5 centimetres per year. Water is released from the subducted plate and lowers the melting temperature of the mantle. Wet magmas rise from the mantle to form magma chambers in the crust below the volcanoes. Eruptions occur when magma reaches the Earth's surface from the chamber. The Caribbean is no stranger to volcanic eruptions. Indeed, the modern science of volcanology can be said to have begun on the island of Martinique to the south of Montserrat. In 1902, Mont Pelée erupted catastrophically and terribly, destroying the town of Saint-Pierre and killing 30,000 people. This was one of the great volcanic disasters of history, and was the first occasion when the deadly phenomenon of pyroclastic flows was recognized by French scientists. They described the flows as nuées ardentes, or glowing clouds. Montserrat is a British dependent territory, first settled as an empty island in 1632. Before the eruption, the island had a population of about 12,000. The picturesque capital of Plymouth on the western coast formed the focus of a successful and thriving island society. Although Hurricane Hugo in 1989 had set the island back, by 1995 the island economy was more or less self-sufficient. There was a rice mill, several cottage industries, a large population of North American and British expatriates, and a large American medical school with 600 students. Montserrat was known as the Emerald Isle and had a reputation for being a friendly and relaxed place, often referred to as the way the Caribbean used to be. Thus a good tourist trade was established, and the island had attracted the likes of Sting, the Beatles, Eric Clapton and Stevie Wonder to the famous Air Studios. Unfortunately, the richest farmland was on the flanks of the volcano, and the south was the most attractive place to live. The Soufriere Hills was already recognised as a young volcano. The volcano consisted of a cluster of andesite lava domes forming several rugged peaks. It was surrounded by gentler flanks of pyroclastic deposits. The volcano dates back to about 100,000 years. A large segment failed about 4,000 years ago in a great landslide. This left a horseshoe-shaped depression with a diameter of 1 kilometre, crater walls of 100 to 150 metres high, and open to the east. This feature was known as English's crater. The flanks of the volcano were cut by deep canyons, locally known as guts. Earthquakes above background levels for a volcanic region were first noticed in 1992 by scientists from the University of the West Indies. Between 1992 and July 1995, there were 18 periods of intense earthquake activity. There had been previous periods of earthquakes in the 1890s, 1930s and 1960s, which had not led to eruption. So the earthquakes were not immediately related to this upcoming eruption. On July the 18th, 1995, steam vents started up in English's crater and the eruption began. For the first 4 months, activity consisted of intense felt earthquakes, steam jets and explosions of increasing intensity. The earthquakes occurred, as can be seen on the map, both below the volcano and beneath a hill 5 kilometres to the northwest. They were located at depths of up to 6 kilometres, and their alignment suggested a northeast tectonic control. The earthquakes were caused by rising magma breaking a path to the surface. Steam vents and phreatic explosions were also caused by rising magma. Groundwaters became superheated and vented from newly formed fractures in English's crater. More violent eruptions, known as phreatic explosions, became more vigorous during August, with production of much ash. Ground-hugging density currents of ash known as base surges swept down the flanks of the volcano. One particularly large base surge swept through Plymouth on August 21st, 1995, and resulted in panic and spontaneous evacuation of the town. Fortunately, base surges are cold, so there were no casualties. The andesite magma reached the surface in English's crater on 15th of November 1995, and a lava dome began to grow. An andesite lava is very different to a basaltic lava. You will be familiar with the behaviour of basaltic volcanoes such as Kilauea on Hawaii. Basalt magma is very fluid and gases escape easily, producing spectacular fire fountains. The 1200 degrees centigrade basalt lava flows easily down the mountain in fast-moving streams that can move many kilometres. Andesite magma is much cooler, 850 degrees centigrade in the case of the Soufriere Hills, and contains high contents of volcanic gas. By the time the magma reaches the Earth's surface, the magma is virtually a hot crystalline solid with a viscosity about 1 billion times greater than basalt. The lava is so stiff that it piles up over the conduit to form a lava dome. The Soufriere Hills eruption allows us to understand how a dome grows. For the first several months of the eruption, the dome grew relentlessly, increasing in size by tens to hundreds of thousands of cubic metres per day. The new lava piles up at the top of the dome. Sometimes new lava is pushed along ductile shear zones to the surface to form great spines and pinnacles. The whole lava has a blocky, fragmented appearance. During the day it looks like a great grey pile of rubble. At night the dome glows. The dome is very unstable, and newly erupted lava near the summit breaks up and rolls down the side of the dome. Such rockfall activity is almost continuous. A talus of rock debris forms at the base of the dome. Let us now leave the dome, growing for a while, and find out what andesite is and how we can use petrology to discover more about the Soufriere Hills volcano. We've come here to consider the petrology and chemistry of the andesite from the Soufriere Hills. It's a pretty typical orogenic andesite lava. It's pretty crystal rich, about 70%, and on this outcrop you can see big crystals of hornblende, and you can also see these mafic inclusions. It's now perhaps worth going to look at a hand specimen a little bit more closely to consider the details. The rock is very porphyritic. It's got about 60% silica, crystals of hornblende, dark hornblende, white plagioclase. There's also orthoproxene and magnetite in it. Probably about 70% crystals and only about 30% ground mass or melt. And you can also see an example of one of these mafic inclusions. These are, we believe, very significant for the eruptions. These are very fine-grained, and it looks like they're little bits of basaltic magma which have been mixed into the andesite during the eruption and have quenched to form these fine-grained bodies. And the idea is that the eruption was probably triggered by basalt from deeper in the crust, or perhaps from the upper parts of the mantle, coming up, intersecting this magma body, very crystal-rich magma body, providing heat and gases, stirring it up, and the basalt magma itself broke up to form these mafic inclusions and mixed in. And if we perhaps go back to the outcrop, you can see that these mafic inclusions are actually very common. Really quite a lot of basalt must have been mixed up into the andesite to cause the eruption. We can tell a lot about the conditions of the magma from the phenocrysts. It's got hornblende in, it's also got quartz, so we can tell that the andesite must have crystallized at depths of at least 6 kilometers to stabilize hornblende. It's also got quartz, and in order to have quartz and hornblende, we also need to have temperatures which are no more than 850 degrees centigrade, perhaps a little less. The pyroxenes in this rock also can be used, and they suggest that temperatures are indeed about 850 degrees centigrade. So we think that this magma originated about 6 kilometers beneath the volcano, in agreement with where the earthquakes were at the beginning, and with water pressures probably enough to have about 5% water in the magma and to stabilize hornblende.
By April 1996, the dome had reached a volume of about 25 million cubic meters. A new and deadly phenomenon now started. Substantial sections of the dome were now failing and collapsing to generate larger avalanches known as pyroclastic flows. A pyroclastic flow is a rapidly moving avalanche of hot volcanic debris. As a section of the dome fails, the debris disintegrates to form a mixture of lava blocks and ash. The lava is probably pre-stressed and can contain pressurized gases. Consequently, the avalanche quickly generates a large amount of fine-grained material. Pyroclastic flows consist of 3 parts. The main flow is a dense concentrated avalanche of blocks and ash. Above the flow, a dense turbulent cloud of ash, volcanic gas, and hot air develops. The overlying cloud forms both by mixing with the surrounding air and by expansion of pressurized gases from the disintegration of lava in the flow. One part of the overlying cloud remains denser than air and is known as a pyroclastic surge. This moves like a density current. While the dense avalanche is confined to the base of the valley, the overlying surge can sweep up valley sides and can detach from the parent avalanche to inundate different areas. Another part of the overlying cloud has mixed with and heated so much air that it becomes lighter than air. A buoyant plume of fine ash and hot air rises above the flow, often to heights of a few kilometers. During 1996, the dome increased in size, and the collapses became larger. By May 1996, the flows started to reach the east coast of Montserrat and enter the sea. Some of these flows were captured by Dave Williams of the Montserrat Volcano Observatory in unique footage from the observatory helicopter. The flows moved into the ocean, and the lower density surge cloud spreads several hundred meters across the sea. The rapid mixture of hot pyroclastic material and water causes small explosions at the flow front. By September 1996, a fan of pyroclastic flow deposits had extended the coastline of Montserrat by over 600 meters. After a period of slow growth at the end of 1996, the dome reinvigorated in 1997, and the dome had a more or less filled English's crater by March 1997. The map shows the distribution of pyroclastic flow deposits in April 1997. The red areas show the pyroclastic flow deposits within the Tar River Valley, moving out to the east of the dome and forming the delta. The Tar River Valley pyroclastic flows were in place during 1996. The blue areas show the pyroclastic flow deposits emplaced within the White River in March and April 1997, as the dome overwhelmed the walls of English's crater. By May 1997, the dome started to overwhelm the northern wall, and pyroclastic flows snaked down the valleys. In the film that you are watching, there is an eerie silence as a medium-sized flow advances down the valley. By mid-1997, the dome was over 60 million cubic metres in volume, and collapses were becoming larger and larger. We will now have a closer look at two major collapses on June 25th and September 21st, 1997. Let's look at a map showing the distribution of the 25th of June pyroclastic flow deposits. The main avalanche deposit in red is confined to the valley leading to the airport on the northeast coast. The surge deposits are mapped in pink. As the main dense avalanche part of the flow sweeps down the volcano within a deep canyon, the surge detached from the flow at a bend and swept over the northern flanks. Tragically, 19 people lost their lives. The surge also transformed into another dense flow known as a secondary pyroclastic flow by a process of rapid sedimentation. The map shows that the secondary flow moved down this other valley 3 kilometres to the west in a direction quite opposite to the main flow. We're at a position overlooking Bramble Airport, which was evacuated on the 25th of June. You can see behind Bramble Airport the areas devastated by pyroclastic flows on the 25th of June 1997 and the 21st of September 1997. There was a community over there called Spanish Point, which is now buried underneath the pyroclastic flow deposits. On June the 25th, the pyroclastic flows nearly reached the airport. About 5 million cubic metres of material avalanched down in about 20 minutes. And the pyroclastic flows came down the valleys at speeds of something like 30 metres per second. That's about 100 kilometres per hour. As they swept down the valleys, the pyroclastic surge clouds set some of the houses on fire and also created a tremendous amount of destruction. The pyroclastic flows swept across the plain in front of the airport and partly buried the town of Spanish Point. 21st of September 1997, there was an even bigger pyroclastic flow, about 9 million cubic metres, and that one did reach the airport and it completely buried the community of Spanish Point. So what we're going to do now is we're going to go down to the airport and have a little bit closer look at both the devastation and also look at the pyroclastic flow deposits. Okay, I'm standing at the end of the pyroclastic flow deposit from the 21st of September collapse in 1997. This is the collapse that destroyed the airport, and you can see the airport terminal building in front of me. Also behind you can see the dome, and although I'm standing in August 1998, the dome in September 1997 was probably pretty similar to then in terms of size. And about 9 million cubic metres of the dome fell off down those valleys. There's a valley there called Chewit's Gut. It fell down that valley and the dome rock disintegrated into a pyroclastic flow, and that pyroclastic flow came down here probably at speeds something like 30-35 metres per second, and came right through the airport terminal, came right through the buildings and ended just here. And you can see that the airport building has been really pretty well destroyed, so even at the very edge, at the end of the flow, when it's running out of energy, it's enormously destructive. Okay, well, we've had a look at the deposit here, so we can now go up onto the flow deposits and see what that's like. Well, it looks like the MVO helicopters in action doing some monitoring work on the volcano as we're standing here on the pyroclastic flow deposits from the September 21st eruption. And you can see here a typical very large block that's formed from the dome. As the dome avalanches, it breaks up into large blocks, but it also disintegrates into a lot of fine grain material. And as I pick this up, you can see that actually much of the pyroclastic flow deposit is really very fine ash and smaller bits of rock. And just away from me, further down, you can see the typical appearance of this blocky terrain of the pyroclastic flow, deposit. You can also see that it's partly buried an old sugar mill as it's come down in this area near the airport. Okay, we're on the 21st of September pyroclastic flow deposit by a large boulder, and what I want to show you is some friction marks related to the tumbling of the boulder as it moves in the pyroclastic flow. We can see one of these friction marks coming down this boulder from here to here. These friction marks, if you look at them reasonably closely, you can see that they actually are slicken-sided, polished surfaces, and you can see these striations going down here. They represent where this boulder exerted all its weight on a neighbouring boulder, or perhaps on the bedrock, and resulted in very, very high pressures and essentially very strong shear friction, producing the marks. So it represents tumbling of the boulder as it moves within the pyroclastic flow, and the pyroclastic flow moves down the mountainside.
The first explosive eruption on Montserrat occurred on 17th of September 1996. Major explosions occurred again in early August 1997. Between the 21st of September and 22nd of October 1997, there were 74 successive explosions, one every 9 hours. Andesite magma is rich in gas. The gas is mostly water, but there is also sulfur dioxide and chlorine. This gas leaks out as the magma rises. At the Soufriere Hills, explosions are triggered by large collapses of the dome. The sudden failures reduce the overburden pressure so that the pressurized gassy magma can explode. We will now look at some of the spectacular explosions from October 1997. An explosion begins when magma with 2 or 3 weight % water reaches an excess pressure of a few megapascals, or typically 30 to 40 atmospheres. The magma spontaneously expands and fragments. The exploding mixture accelerates to velocities of about 200 meters per second. Large meter-sized blocks known as ballistics are ejected at speeds of 100 to 150 meters per second, reaching distances of 1.5 kilometers. Part of the erupted mixture is denser than the atmosphere and runs out of kinetic energy about 300 meters above the vent. This mixture falls back like a huge fountain. From such a fountain, another kind of pyroclastic flow is generated. These flows are composed of lumps of pumice and ash. Pumice is inflated magma full of gas bubbles. The flows move down all sides of the volcano. Initially, their velocities are perhaps as much as 60 or 70 meters per second, but they slow down and move forward at a more sedate speed of about 10 meters per second down the valleys. Some of the erupted mixture has mixed with enough air to become buoyant, so that a plume of pumice, ash and air also rises to heights of about 14 kilometers during one of these explosions. The ejector is then spread by winds over the island. Let us sit back and admire explosive activity in pyroclastic flow formation on Montserrat, including some shots at night, which show ballistic blocks, glowing pyroclastic flows, and lightning playing on the column surface. During the film, you can hear the noise of a scanner recording continuous seismic energy made by the explosion.
Be careful, guys. Volcano. Well, this is the top of the eruption column as the sun hits it at maybe 12,000 feet or so. I'm amazed. Totally amazed.
Explosive activity produces fragments ranging from large metre-sized blocks to fine dust. Much of the ejecta is between a few centimetres and a few millimetres, fragments known as lapilli. We can see fallout on a car roof, and pumice lapilli are raining out. The deposit is quite well sorted, in that the deposit has a restricted range of sizes. Coarse blocks land only close to the volcano, whereas fine ash is swept away many tens of kilometres. One of the major processes in Montserrat is the fallout of ash from the volcanic plumes that form both from pyroclastic flows and from explosions. Much of the ash that fell over Montserrat came from the pyroclastic flows. And what happens is that as the pyroclastic flows come down the valley, the blocks disintegrate and release the gases from the pores, and this flushes out the finest grained material and forms a plume above the flow, which can rise up to a few kilometres above the pyroclastic flow. The winds then drift this plume over the island and generate ashfall deposits. Ashfall deposits characteristically drape the topography, and because the winds in this part of the world are very largely from east to west, it turned out that most of the ashfall accumulated in the Plymouth area on the western side. And I'm in the outskirts of Plymouth here, and you can see here during the course of the eruption about 30 centimetres of fine-grained ashfall has accumulated. This is typical of the ashfall from the pyroclastic flows. Over 90% of it is less than a millimetre, very fine-grained. Now, ashfall deposits create a number of hazards, and one of those hazards is illustrated here with this house. You can see that the 30 centimetres or so of ash has accumulated on the sides of the house, but the roof hasn't collapsed because the roof is too steep. But the neighbouring house hasn't fared so well. The roof is flatter, and therefore the accumulation of ash has weighed down on the roof, and it's started to fail and bow down. And on other parts of Montserrat, of course, you can find roofs which have completely collapsed under the weight of the ash. Another hazard relates to possible health problems. The lava dome contains a form of crystalline silica known as cristobalite. This forms from the volcanic gases in pores, and when the pyroclastic flows come down the valley, this cristobalite is crushed, and it ends up in the finest grain micron-sized dust in the ash, the kind of ash dust that you can breathe in. And the crystalline silica can cause health problems if people are exposed to it for a long period of time. Okay, well, you've seen the explosive activity from September and October 1997, with the explosive eruptions producing fountains of material which collapse, and out of this collapsed material come pyroclastic flows which go down all the valleys of the volcano. Well, I'm now standing at the deposits produced by these pyroclastic flows. You recollect that they move at quite slowly, perhaps 6, 7, 8 meters per second, and they're made mostly of pumice fragments like these ones, quite light, and ash, and as they flow they produce a very characteristic leve and channel morphology. I'm at the margins of the flow where there's what we call a levee. It's a high strand of pumice, and what's happened is that as the flow moves along, the lighter pumice moves to the top and then it's shoved out of the way by the advancing flow, and it leaves a levee. I'm going to pick up a couple of rocks to show you when I get down there. Now we can look at some of the material. This is a lump of pumice. You can see the vesicles, the gas bubbles. This material is actually quite light. My guess it's about 1,200, 1,300 kilograms per cubic metre. It won't float, but it's not far off, and it's really quite light material. You also get another kind of pumice quite commonly. This one, you can see that the gas bubbles this time, the vesicles, have been stretched by flow in the conduit, deformed during rise from depth, so by some kind of shear flow. So that's the typical material from a pyroclastic flow formed by an explosive eruption at the Soufriere Hills.
The largest volcanic event of the eruption occurred on the 26th of December 1997. In 1996, the southwest wall of English's crater became unstable. The village of St Patrick's on the west coast was threatened and was evacuated. Over a year later, at 3 a.m. on the 26th of December 1997, the wall failed. A debris avalanche, also known as a volcanic landslide, of hydrothermally altered and weathered rock flowed towards the sea. At the same time, by far the largest collapse of the dome occurred, involving 60 million cubic metres of lava. A highly energetic pyroclastic surge swept over the flanks at speeds of up to 300 kilometres per hour. 10 square kilometres of southern Montserrat was devastated, including the village of St Patrick's. We will now examine the debris avalanche and the effects of the pyroclastic surge in the field.
I'm in the upper parts of St Patrick's village, and I'm looking towards the volcano, which is in cloud at the moment, but what I want to draw your attention to is this rather hummocky terrain with lots of different coloured rocks, oranges and greys and greens and whites and pinks. This is the debris avalanche from the 26th of December 1997 eruption. What happened was that after 24 hours of earthquake activity at 3 in the morning, an area up in the upper flanks of the volcano, a fumoloric area of hydrothermally altered rocks, failed, and about 45 million cubic metres of material swept down to the sea and also swept over into this area and produced this very nice debris avalanche deposit. All the different colours represent the hydrothermally altered rocks, and we're now going to go up there and have a little bit closer look at the debris avalanche deposit. I'm at the flow front of the debris avalanche from the 26th of December eruption. As you can see, the debris avalanche is made of this hummocky terrain, a volcanic breccia made predominantly of very hydrothermally altered rocks, producing this remarkable display of colours. The problem with a volcano like this is that very often the hydrothermally altered areas are areas of weakness, and we believe that that's why this area failed to produce the debris avalanche. In actual fact, this whole area up on the flanks of the volcano had been unstable since October 1996, so it took over a year before the main failure actually took place. I'm now going to bring you over some rocks from the debris avalanche to look at some of these hydrothermally altered materials. Here's some samples around here. This is an example of the fresh dome rock. It's completely unaltered. Nice fresh minerals, but the other three samples are essentially from the debris avalanche and are heavily altered. One of them's got deep red-brown colours, which represents hydrothermal alteration, iron oxides. Another one's gone to this white mineral, possibly some kind of sulfate, and then you can see this one has got some yellow sulphur on it, again from the hot spring areas, and these rocks make up the debris avalanche deposit. The 26th of December eruption was an example of the most lethal kind of volcanic phenomena. An explosive and highly energetic current expands laterally and destroys almost everything in the way. Such a pyroclastic surge or volcanic blast destroyed Saint-Pierre in Martinique in 1902 and devastated 600 square kilometres round Mount St Helens in 1980. The collapse of the lava dome at the Soufriere Hills on the 26th of December 1997 resulted in the high pressure gases within the dome expanding explosively to form a pyroclastic surge. Such pyroclastic surges are largely erosive near the volcano and only leaves thin deposits. We will now go to look at some of the remarkable effects of a pyroclastic surge.
You can see in this house that the whole top floor of the house has been stripped off by the pyroclastic surge. You can see here a pillar that's broken off, and you can see the bits of debris from the top floor have been strung out downstream of the house. And now we're going to go back and look at behind the house where we can see some impact structures. We're at the side of a house which is affected by the 26th of December pyroclastic surge. The surge picked up boulders, and these boulders impacted the wall of the house. Mostly they bounced out, but in this case a big rock has actually implanted itself in the wall of the house, and in fact the whole upper floor of the house has been swept away, and you can see these impact marks from boulders from the surge. We can now go into the house and see what happened in the dining room. So we're going into the dining room. Surprisingly, the table's almost set for dinner. There's been no disturbance, and all that's happened is a lot of ash from the surge has come into the room and spread over the room, but you can see that the dining room is pretty well undisturbed despite the mayhem outside. You can see that the ash that comes in is very mobile. If I step on it, bits of it blow out, and it's very mobile. Pyroclastic surges are tremendously powerful. They can take up large objects and hurl them surprising distances. This is a bulldozer, and this bulldozer was hurled over that cliff behind me from a haulage yard about 200 metres inland. You can also see on the road up below the cliffs the remnants of a mangled truck which was also hurled over the cliff. I'm about 2 kilometres from the lava dome, which was the source of the very energetic pyroclastic surge on the 26th of December. And although in this very proximal area these pyroclastic surges are so energetic they're largely erosive, locally they do produce depositional features. And here's one example, which is a very beautiful gravel bar. As you can see, it's made of coarse-grained breccia. It's about 40 metres long, a couple of metres high, and about 5 metres wide. And this is streamlined in the downflow direction. In actual fact, it very much reminds me of the kind of gravel bars you get in braided river systems in flash floods, where you get similar bars streamlined in the downflow direction. And at the end you can see that the gravel bar is again streamlined and eroded, and it comes to a termination about there. One of the most remarkable features of the pyroclastic surge is that when it came through and eroded in this area, it also left behind a blackened and eroded surface. The surface is scoured, and when you look in detail and pick up a little bit, you find that it's actually a tar. There's about a 3 or 4 millimetre layer of tar across the entire area, probably about 4 or 5 square kilometres. And we think that this is due to almost instantaneous incineration of the vegetation as the surge came through. This is what the pyroclastic surge did to a tree in the area of severe damage. The tree is completely gone, and all we've got is the stump, which is about 1 metre in diameter, and it's been severely abraded. Another interesting feature you can see here is that a bit of rock from the surge has embedded itself into this tree stump, and it's really quite firm. I can't really move that out. I'm in the port area of Plymouth. Plymouth, unfortunately, was largely destroyed in July 1997 when pyroclastic flows came through the centre of town.
But that wasn't the end of the story, because during the eruption, something like 100 million cubic meters of loose volcanic debris and ash have on the flanks, and this material is easily remobilized during rainstorms to produce flash floods and also to produce what we call lahars, or volcanic mudflows, flows of volcanic debris and ash, water-laden flows which come down the side of the volcano, and these still can be immensely destructive. In fact, quite a lot of Plymouth has, even though the eruption has stopped, been continued to be destroyed because of the effect of lahars.
A lahar is a rapidly moving slurry of sand, gravel and boulders mixed up with water. The debris is remobilized off the mountain and flows down the valleys and spreads out with high speeds. In the footage you are watching, large boulders jostle against each other in the lahar, and it is easy to imagine that a lahar can impart severe damage on structures. In these pictures in 1995, a flash flood full of volcanic debris moves down the main river valley through the centre of Plymouth. As the eruption proceeded, the valley was filled with laharic debris and pyroclastic flow deposits. Now you can see the same location with the bridge buried under 10 metres of lahar and pyroclastic debris. In central Plymouth, buildings have been almost completely buried. At the prison you can see the wire at the top of the prison compound. In 1998, high rainfall during the hurricane season caused further lahars and added several more metres of deposits in Plymouth, as is evident in footage from February 1999. Having looked at the volcanic phenomena, let us now consider monitoring methods. Seismology is at the heart of a functioning observatory. Earthquakes give an instant measure of activity. Scientists at the Montserrat Volcano Observatory have learned to recognise several kinds of earthquakes from their network of 11 seismometers on the volcano. Each of these earthquakes relates to a different kind of activity. Volcano-tectonic earthquakes have very sharp onsets and distinct P and S arrivals. They also have predominantly high frequencies. They are formed by rocks breaking and shearing as magma ascends. Volcano-tectonic earthquakes occurred mostly before the dome appeared at the surface. Hybrid earthquakes have both low and high frequencies and are associated with active dome growth. The lower frequencies are thought to form by resonation of high-pressure gases escaping from the rising magma along cracks. Long-period earthquakes have only low frequencies. They are sometimes observed to form when gas and ash escapes as jets from the dome's surface. Rockfall and pyroclastic flow seismic signals are cigar-shaped, slowly building up and then dying out. They typically last tens of seconds. Rockfall and pyroclastic flow signals occur when the dome is growing.
We've come to the south of the volcano by helicopter to look at other kinds of monitoring technique, and in particular ground deformation. When the volcano is very active, the sides of the volcano swell out because of the internal pressure, and as a result the volcano deforms. And there are now available a range of sophisticated techniques which enable you to measure the very small movements that take place due to the pressure inside the volcano. My colleague here, Dr. Richard Hurd from the British Geological Survey, is setting up GPS equipment, and I'm going to ask Ricky to explain to you something about the techniques and the kinds of measurements that we've got on Montserrat.
Okay, there are three main techniques that we use for monitoring the deformation of the volcano. One technique which we have here is the GPS system, which uses the satellites, and we can measure over a number of stations on the volcano. We can measure the positions of all the sites on the flanks to within a centimetre or so of one another. And we measure those repeatedly and see how the volcano expands and contracts and how parts of it move with time. We also use reflective glass prisms, which are very high up on the volcano, and we shoot those with a modulated laser, and the instrument measures to within a few millimeters. You can measure the distance between you and the reflector. And the third technique we have is electronic tilt meters, which they have a radio signal which goes back to the observatory, and you can use those to measure very accurately the inflation and deflation high up on the flanks of the volcano, and it can tell you about pressure changes, and we get a signal from those every minute or so. The results we've had on Soufriere Hills, the main GPS results have been quite a restricted amount of deformation, but the period of highest activity last summer and autumn, we had quite rapid shortening on many of the lines as the volcano expanded, and a portion of the volcano on the east side was moving away from the center of the dome. The electronic tilt meters which we have, they show quite rapid inflation and deflation over about a 10-hour period or so in response to the hybrid earthquake swarms that we have.
This is the correlation spectrometer, which allows us to measure from the helicopter the flux of volcanic gas from the volcano. In particular, it measures sulfur dioxide. The instrument consists of a tube here which is directed up to the sun. An ultraviolet light comes from the sun through the tube, reflected off a mirror into the instrument. Now, ultraviolet light is absorbed by the sulfur dioxide molecules in the gas plume, and so the instrument basically measures the amount of absorption and measures therefore the amount of SO2 molecules coming off the volcano. By flying this instrument steadily underneath the volcanic plume, we can get an idea of the sulfur dioxide flux. And I'm just going to ask my colleague Tapi Sayers about what they've been seeing recently on the volcano.
Okay, well, last week we measured the flux at about, let's say, 1,000 tons per day. So we're just going up now to check and see if that trend has continued.
The impact of the eruption on the people of Montserrat has been considerable. As the eruption slowly escalated, increasing areas of Montserrat were threatened and had to be evacuated. The economy of the island deteriorated as key infrastructures such as the port in Plymouth, the airport and the rice mill had to be abandoned. The scientific team at the observatory converted their observations and understanding of the volcano into hazard and risk maps, which assisted the authorities to manage the crisis and make difficult decisions. The scientists also became involved in communication with the public to explain what was happening on the volcano. The island was too small to accommodate all the displaced people. Many Montserratians had to leave their homeland for Britain, North America, or other Caribbean countries, or had to live in primitive shelters on the north of the island. By 1998, only 4,000 people of the original 12,000 population remained on Montserrat. However, those remaining are resilient and are now determined to rebuild the island's society.
In March of 1998, the dome growth stopped, and it looked as though the eruption had ended. For many months, very little happened, but volcanic gases continued to be discharged, and there were numerous small explosive events. The MVO observed from GPS measurements that the ground was slowly rising, and this indicated that the magma chamber was still active. In November of 1999, after a lull of almost 19 months, a swarm of earthquakes led to the resumption of dome growth. A second major phase of the eruption had begun. Dome growth continued for another 4 years, with the dome reaching a significantly greater size than any of the domes that grew in the 1995 to 1998 period. During this time, there were further dome collapses, producing pyroclastic flows that snaked down the valleys, some reaching the sea by way of the Tar River Valley. When the weather was clear, it was possible to see the ongoing rockfalls and pyroclastic flows from many vantage points on the east and northwest sides of the volcano. At night, the views were even more spectacular, with almost constant flows of hot rocks and gases cascading down the sides of the dome. By May of 2003, the dome's summit was 1,100 meters above sea level and 190 meters higher than Chance's Peak, previously the highest point in Montserrat. With a volume of about 200 million cubic meters, it was almost twice the size of the largest dome of 1998. This prolonged activity meant that scientists would be carefully monitoring the volcano for the foreseeable future. Thus, a new, state-of-the-art volcano observatory was built as a permanent home for the MVO. It was opened in December 2002. It was about this time that the large size of the dome began to threaten the safety of those who were living along the sides of the Belém Valley. It was decided that these people could be in danger should the dome collapse to the northwest, so, for safety's sake, this area was temporarily evacuated in October of 2002. Then on the 12th of July, 2003, during a heavy rainstorm and elevated seismicity, the weakened dome structure finally collapsed down the valleys to the east and northeast of the volcano. This led to a series of explosive events that showered the entire island with fragments of dome rock and pumice clasts ranging in size from a few millimeters to 5 or 6 centimeters. As you can see by these before and after pictures, about 2/3 of the 200 million cubic meters of dome material disappeared. This event is now recognized as the largest dome collapse in recorded history. The ashfall measured up to 15 centimeters or 6 inches deep in the hardest hit areas to the northwest of the volcano, breaking down tree limbs and making the whole island look like a black and white photo. The static electricity in the smaller particles created an amazing display of lightning and thunder that could be seen like a fiery curtain drifting out over the sea for many miles to the west. With the dome gone, the volcano became more and more quiet, reducing the risk and enabling the most recently evacuated areas to be reoccupied. The staff of the MVO continue to keep a close eye on the Soufriere Hills, and every 6 months, a team of scientists from around the world meet with the regular staff to assess the hazards and risks of the volcano and to share their collective, objective views of what the future might hold. During the rainy seasons, successive mudflows have continued to bury the capital city of Plymouth in 20 to 30 feet of lahar material. Even the well-known War Memorial was knocked down by the force of the flows, with only the top of the tower surviving to be carried almost 100 meters down towards the sea. On a positive note, tours of the buried city are now being arranged by the Tourist Bureau, and this could be a big boost to the future of tourism in Montserrat. In November of 2003, a major cleanup program was initiated, and after almost 6 months of constant cleaning, things really began to return to normal. As each month passes, the people of Montserrat become more and more hopeful that the volcano might really be going back to sleep. Everywhere you look, there are positive signs that the island is rising from the ashes of this destructive eruption. The Emerald Isle of the Caribbean is recovering her brilliance. Because volcanic eruptions cannot be controlled, they will always cause severe stress on the people living near the volcano. However, Progress in understanding volcanoes can make societies better prepared to face the dangers and to mitigate the effects of volcanism.
Up here must have been a I got a picture of him in the chopper that's unbelievable.